So, tonight's speaker is a PhD from the University of Illinois. He's been a research fellow at the Los Alamos National Laboratory, fellow in cosmology at Carnegie Mellon University, and research scientist, deputy group leader at the Institute for Theoretical Astrophysics at the University of Heidelberg. He's currently a senior lecturer at the Institute of Cosmology and Gravitation at the University of Portsmouth. Please give a big welcome for Dr. Dan Whalen. Thank you.
Can you hear me in that?
No.
Is this not working?
Oh, is it?
Yeah? It is working. Yeah, we turned it right down, so use as much voice as you like. All right, let me try to project my voice a bit better. If there's a problem, please feel free to raise your hand. And please feel free to raise your hands during my talk. I don't mind turning this into a discussion. So even though I know there'll be a Q&A. So in the introduction, in case you are wondering what a fellow is just a postdoc who doesn't have a boss. And so basically, I really had some nice opportunities to go and work in some positions after I got my PhD. So after you get a PhD in astronomy, in the US that takes typically 5 or 6 years because we start right after undergraduate school. And then we usually do 2 or 3 postdoctoral research appointments. You're an itinerant worker, and you go from place to place every 3 years. So every 3 years, you're putting out 50 job applications. Your letter writers are writing 50 letters for you each, and you just keep doing research and writing papers until hopefully you have a big enough record and enough people have cited you in their papers that you can get a university position. And I'm really grateful to be able to have gotten a university position here in the UK and work on the things that we're working on. So with that, I've got to also make a couple of apologies in advance. So astronomers, we do some strange things. So first, we talk about the largest objects in the universe with the centimeter-gram second system. We don't use meters, kilograms, and seconds, we use centimeters. And this dates back to spectroscopy in the late 1800s, because most of the astronomical, the hard data studies back in those days were done with spectroscopy, and it was all centimeters and grams. So the other thing I need to apologize for is that we have this strange habit of calling any chemical element heavier than helium a metal. So to us, carbon, oxygen, nitrogen, they're all metals. So if I talk about metal production by early supernova, it's just any element heavier than helium. And the reason for that is, during the Big Bang, the densities and temperatures at early times during the Big Bang were so intense that only very simple nuclei emerged from the Big Bang. Just hydrogen, helium, very trace amounts of lithium, even less boron, and nothing really above beryllium. So any of those elements heavier than that came from the interiors of stars later, as we'll discuss if there's time. Okay. And one last thing I have to apologize for. So a logical thing to do when you're talking about the age of the universe is age since the Big Bang, right? That makes sense. Like the first stars we think formed 200 million years after the Big Bang. But astronomers use redshifts. So because and this is again because of history. And it goes back to Edwin Hubble in 1929. So Edwin Hubble was the guy who discovered the expansion of the universe. The fact that very distant galaxies from us, the further away they are from us, the redder their light appears to us to be. And that's not because after the Big Bang, all galaxies blew away from one common point in space. It's because wherever we look in the sky, galaxies are going away from us because the expansion of space and time is literally carrying them away from us over time. Okay, and so the redder an object looks is related to what we call its redshift. It's by how much its light is redshifted to us. Well, why do astronomers, at least until recently, talk about the redshift of a very early object rather than its time after the Big Bang? Well, the answer to that is we didn't know. We didn't know what time after the Big Bang was associated with the redshift of a galaxy. And we didn't find out until 2004. So the expansion of the universe was discovered in 1929. But we didn't know what redshift corresponded to what age since the Big Bang until 2004. And that's because a satellite called WMAP, so WMAP, I apologize for this, stands for Wilkinson Microwave Anisotropy Probe. And what WMAP does, or did, was simply sit out in the Lagrange orbit, so in the Lagrange point between the Earth and the Moon, where it was quiet and cold. And it sat and it watched the microwave sky. And I'll show you in a few minutes the picture it took of the cosmic microwave background of the sky. And from the shape of that background, it was able to pinpoint the age of the universe for the first time. And so our best cosmological models tell us that the universe is 13.87 billion years old. And the objects I'll be discussing tonight, the first quasars, or supermassive black holes, these objects formed during the first billion years of the universe, the age of the universe. In fact, we'll talk about some black holes. Billion solar mass. Again, we can't describe the mass of a black hole in kilograms or pounds, unfortunately. We have to use multiples of the mass of the sun. So when I say a billion solar masses, it means a billion times the mass of our sun, basically. So I'll talk about the origin of billion solar mass black holes that have the diameter of a solar system, but less than a billion years after the Big Bang, and how we think that might have happened, because the existence of these objects poses serious challenges to our understanding of how structure in the universe formed at early times. So, all right, and before I launch into into my talk, I'm going to pose a question to you, and that's this. Let's say that we took the Earth and compressed it down into a black hole. So in principle, it's possible. We don't know how it could happen, but in principle, it could happen. So if we took the Earth and compressed it down until it became a black hole, it would be about the diameter of Winchester. It'd be about the diameter of your city. So fairly compact. Okay, so that's case one. Case two is I take my cell phone and I compress this down into a black hole. So how big would the black hole be that we would form out of this? Well, it'd be microscopic. We couldn't see it with the naked eye. Which black hole would you rather be close to? What do you think? Winchester? Winchester? We'll come back to evaporation in just a second. Yeah. So I've heard some people say Winchester. I've heard some people say the cell phone. Okay, well, I wouldn't want to be close to either one, but I might survive a little longer if I were close to the Winchester black hole. And the reason for it is that so all black holes, let me say it this way, no black hole is truly black. Because Stephen Hawking, back in the 1960s and 70s, found that quantum mechanical processes near the surface of a black hole could cause it to radiate particles. The temperature of those particles is inversely related to the mass of the black hole. So if you have a really big, like a Winchester-sized black hole, that black hole is cold. It doesn't radiate away energy very quickly. If I turn this into a black hole, it would radiate all of the rest mass of this phone away in less than a microsecond. And the energy output would be roughly 30 terajoules. So if you don't know what a joule is, the equivalent is Nagasaki and Hiroshima put together. So if this were suddenly collapsed down to a black hole, it would explode in a flash of particles with the energy of 2 atomic bombs. So really interesting processes can happen with black holes, but we're going to be talking about black holes tonight on the opposite end of the mass scale, the very massive ones. So do you know what the current record holder for the most massive black hole ever detected is to date, at least? Does anybody want to hazard a guess? Huh? Actually, so I'm glad you brought up LIGO. So a couple of years ago, LIGO discovered gravitational waves from the merger of 2 black holes. And those black holes were roughly 20 and 40 solar masses each. And so those are what we call stellar mass black holes. But at the center of our Milky Way, there's a black hole. Have you ever heard of this? It's called Sagittarius A. We call it SAG-A because somebody wants to say Sagittarius A over and over again. So SAG-A, it has a mass of 4 million solar masses. That's actually a pretty small supermassive black hole. The current record holder is 40 billion solar masses. And these massive black holes always reside at the centers of galaxies. We don't find bare supermassive black holes out in the universe. They always form at the centers of galaxies, and that gives us clues about how they came into being in the first place, and I'll discuss this a bit during my talk. So, with that said, if you could look out to really great distances in space, and if you could do it over the entire sky, you would see that the universe looks cobwebby. In other words, galaxies are not uniformly sprinkled through space on large scales. So back in the 1980s, there were some key technological developments. So CCD, charge coupled devices, you know the object that makes our cell phone cameras work today. Well, those were developed by astronomers. And the reason they were developed by astronomers was to be able to look at large areas of the sky and take lots of images of galaxies. Because you can't do that with photographic plates, the old technology, like with Polaroid film. You can't do that. So electronic CCDs were invented by astronomers to look at large areas of the sky back in the 70s and 80s. And when they started to do this, the first what we call deep surveys found that galaxies were not uniformly distributed through space. They actually were sprinkled throughout what we call cosmic filaments and voids. So here, what we see is an image of the Sloan Digital Sky Survey. And the Sloan Digital Sky Survey has been going on strong. It's been going strong for 10 years now. And the longer it looks in the sky, the more galaxies it sees, the greater area it can see. And as you can see, those yellow dots, which are galaxies and clusters of galaxies, they're spread out in this really interesting filament system, and then there are volumes with very few or no galaxies. We call those voids. And so the question is, why do galaxies distribute themselves out in these really unusual patterns in the early universe? Because right after the Big Bang, the universe was really uniform, and it was really kind of boring. I mean, it was super hot and super dense. But as it expanded and grew, there were very few differences from one part of the universe to the other part. So how did this really non-uniform distribution of galaxies emerge from a very, what we call, isotropic Big Bang and uniform early universe? Well, the answer is in two things. Here's a kind of a pie chart of the contents of the universe. And as you can see here, only 4% of the mass and energy content of the universe is in the form of matter we understand, namely atoms, electrons, protons, and neutrons, and the cosmic, like the zoo of elementary particles that you may have heard of, like muons, neutrinos, and all of those things. So 22% of the universe is in the form of what we call dark matter. So people ask me what dark matter is, and I have to reply to them, we don't know yet. In fact, we have these theories in particle physics called superstring theory. Well, actually, supersymmetry theories. Supersymmetry theories predict that every normal elementary particle, elementary particle has a supersymmetric pair. And so some people think that dark matter might be composed of this kind of a subatomic particle called axions. Others think it might be a supersymmetric particle called a neutralino. And if you haven't heard of those particles before, it's because they're esoteric and they haven't been discovered in the laboratory yet. So the answer is we don't know exactly what dark matter is, but we know it has to be there. And do any of you know why we know dark matter has to be out there? Yes?
Galaxies rotate, instead of dying off the velocity, they rotate at a constant velocity out there, and you get gravitational lensing around galaxies, and they calculate from the Big Bang the various peaks for the spectrum.
That's right. And so there's a famous astronomer.
Summarize that, because I don't think everybody heard.
I'm going to. So there's an astronomer named Carl Zwicky, and Carl Zwicky and others looked at the rotation of distant galaxies. So how can you tell? How can you measure how quickly a distant galaxy is rotating? Redshift, the Doppler shifts. In general, yes, exactly. So if you look at one part of the galaxy that's coming towards you, light from that, if you can resolve it, you have to see the galaxy as a shape. If you can see it as a shape, light from one side of it might appear a little bluer because it's rotating towards you. Light from the other side of the galaxy might be a little redder because it's going away from you. And then we call that, it's due to something called the Doppler shift. And so by measuring those two Doppler shifts, we can tell how quickly a galaxy is rotating. Well, we can also tell how much mass there is in a galaxy because we can measure the light coming from the galaxy, because there's a fairly good correspondence between light coming from a galaxy and the total normal mass coming from the galaxy in terms of stars. Stellar budget, we call it. And when we did the math, we found that they were off by a factor of 10. In other words, stars in the outer rim of the galaxy were rotating at much higher velocities than the mass we could see in the galaxies could account for. By all accounts, those galaxies should have been flying apart. And it was then understood that for all the visible matter that we saw in the galaxy, there had to be 7 to 10 times more matter that we could not see. And it was not just because the matter was dark. In other words, it's not because that matter was not emitting photons. It was much stranger than that. It's because that matter could not emit photons. It was not capable of emitting photons. And what I mean by this is the following. If you can, and I'll give you the 30-second version of this. So when I touch the table, what prevents my fingers from going through the table? Well, on the subatomic level, it's because electrons in my fingertips are exchanging photons like a game of catch with baseball. They're exchanging photons with electrons on the table. And that's how elementary particles feel each other. They exchange particles. In this case, light. Well, whatever dark matter is composed of, it cannot emit or capture photons. And we know of no elementary particle in nature that can do that. And so that's why we've been looking for candidates for dark matter in the Large Hadron Collider in CERN in Switzerland. One of the great promises of the LHC, the Large Hadron Collider, was that it would discover supersymmetry. It would discover, well, there were three great promises. One is that it would find the Higgs particle. And if you've never heard of the Higgs particle, just think of the Higgs particle as being the particle that gives all the other particles in nature their masses. It's why they feel mass. It's why those particles have a mass. And now, LHC found the Higgs, and some people won the Nobel Prize for that. Secondly, The other great promise, another great promise of the LHC is it would discover supersymmetric particles. It could access the energy scales at which supersymmetric particles would appear. It has not. So have you ever heard of superstring theory? Superstring theory took a body blow because of that. Because superstring theory is based on supersymmetry. And the LHC has ruled out the simplest case of supersymmetry. It doesn't mean that superstring theory is dead, but people are not being hired in faculties in universities as quickly as they used to be in superstring theory because of that. So a great promise of LHC was that it would find something called extra large dimensions that we don't have time to go into now. And it did not find them, probably because either they're not there or they could not be accessed at the energy scales LHC could deliver. So anyway, to cut the story short, we don't know what dark matter is, but we know it has to be out there. And not just because of the rotation curves of galaxies. We can now watch the dynamics of galaxies in clusters of galaxies. And we find that they're being bound together by much more mass than is visible in the entire cluster. So not only does dark matter reside in galaxies, but it fills the space between galaxies, binding those galaxies together in clusters. Okay, well now 74% of the universe in terms of mass energy content, and here we're talking about the energy side of it, is in something called dark energy. And if you thought dark matter was strange, dark energy is much stranger. And literally we do not know, we don't even have a clue as to what it is. Neither in astronomy nor in particle physics. And so I would say that this is one, if I had to name one of the top 5 problems in physics today, it's the nature of dark energy. And some people would put it as number 1. So what is this dark energy stuff? Okay, remember how I told you that Edwin Hubble found that the universe was expanding, which was a shock to the community in 1929. And well, all the cosmological models, and when I say a cosmological model, I mean the models that predict the dynamics of the expansion or the contraction of the universe as a whole. All those dynamical models assumed that as the universe was expanding, it was slowing down. That was just gospel for over 50 years, 60 years. And so, but what happened was, in the mid-1990s, 2 teams, one team from Lawrence Berkeley National Lab and another from Harvard, decided to do precision measurements of what we call type 1a supernova explosions. So type 1a supernova are exploding stars. They're the thermonuclear detonations of carbon-oxygen white dwarf stars. And they're very special explosions because they all explode with about the same energy. And because they explode with about the same energy, when one goes off, if you measure how bright it is, you know how far away it is. We can't do that with core collapse supernova or any other kind of stellar explosion. Well, these guys decided to measure a bunch of type 1a supernova, and what they found was the further out you went, the light coming from those supernova was redder than they anticipated it would be, meaning that those stars, those explosions were being carried away from us faster than any of the cosmological models had predicted. And that blew everybody away, because it meant that instead of slowing down as the universe expanded, it's speeding up. And cosmological acceleration, which is what we call it, means that one day we will see no more galaxies. In whatever direction the sky will look at, we won't see another galaxy, because the expansion of the universe has carried them so far away from us so quickly that light from those galaxies can't travel back fast enough to get to us. If our current understanding of our observations is correct. Of course, that was a complete revolution in astronomy that earned the discoverers the Nobel Prize a few years ago, right before gravitational waves was awarded the Nobel Prize. All right, why do I go through the energy content of the universe? Because it accounts for how galaxies are distributed non-uniformly on the sky. When the Big Bang happened, the universe was hot and mostly uniform. Departures from uniformity and density from place to place in the universe were less than 1 part in 100,000. So there were little dimples in density in the universe, and they were randomly, we say Gaussian, they had a Gaussian distribution through space. They were randomly distributed through space. But what happened is, and why was the universe a bit dimpled? The quantum mechanics of quantum field theories in the early universe. The quantum fields that drove inflation, for example, things unfortunately we don't have time to go into tonight. But I can discuss with you offline later if you want. Well, quantum mechanics put little tiny dimples in the universe all over the place, and they were uniformly sprinkled. But as the universe expanded and cooled, gravity collapsed those dimples into denser and denser and denser structures over time. And then gravity also congregated those dimples into the cobwebby appearance that we see in the distribution of galaxies on the sky in the deep surveys. So it's basically the dynamics of dark matter and dark energy that govern how galaxies form and how they're distributed on the sky. Okay, so that's a lot of detail to digest, and if you haven't digested all of it, it's okay because I'm going to go through it again. It's going to come up again as I go through the talk. But why do I talk about the ingredients of structure formation in the early universe? So remember I talked about WMAP. Think of this as a baby picture of the universe. What you're seeing here are hot spots and cold spots in the cosmic microwave background, photons on the sky. So, if you remember your TV sets before they were flat screens and we had UHF and VHF channels. So I remember this when I was little, and when you turn on I shouldn't betray my age, I guess, but anyway, when you turn on a UHF channel that's empty, what did you see? You saw snow on Hatch, right? Some of that was cosmic microwave background photons that you were seeing. So you were seeing echoes from the Big Bang on your H channel on TV. So anyway, the difference between a red hotspot and a blue hotspot there is only 1 part in 100,000. This is why WMAP had to look at the sky for 4 years to create that map, because it had to sit and collect enough photons, enough photons, enough photons over time to get to dial down the signal-to-noise ratio to see those small departures from uniformity. So those hot spots and cold spots led to the cosmic web of galaxies and clusters of galaxies we observe today. All right, so, and this is how it happened. Here's a supercomputer simulation of the collapse of dark matter into galaxies and clusters of galaxies in a large volume. So the length of that cube is probably a couple of 100 million light years on the side. And you're seeing how so we have supercomputers now that can take a box 1 billion light years on a side and evolve the universe from the Big Bang down to today in a couple months. And here you can see how that dark matter and gas collapsed into this cosmic web of structures we see today.
How many points of mass would there be in
These are typically, this is an older simulation. I would say this is probably on the order of 10 million particles. We can now do tens or even hundreds of billions with supercomputers. Yeah. And actually supercomputing is what I do. So I do numerical simulations like this. All right, now, because I'm a scientist, I'm obliged to put one plot up on my talk. So don't worry about digesting this, but if you study this long enough, you would see that at very early times, the universe was dotted with lots of little clumps of dark matter and gas together. And we call these gravitationally bound clumps of dark matter and primordial hydrogen helium, we call them halos. So primordial halos. And think of a primordial halo as a small pre-galactic structure. And the reason I put this plot up is to show or quantify that structure formation in the primitive universe is hierarchical, in the sense that at early times in the universe, the universe was dotted with lots of little low-mass halos. But over time, those halos merged through gravity and grew into ever and ever larger structures down through cosmic time. So that today, there are far fewer small halos because they've all been congregated into massive galaxies today. And that's what happens. And so these actually are called the crescendo curves, and it's something that every new PhD student in astronomy learns. Okay, now let's talk about the appearance of the first luminous objects in the universe, because this is going to take us into the origin of the first supermassive black holes. And let me see how I'm doing on time. Okay. All right, so here, this is a numerical simulation of dark matter collapsing into a primordial star. And as you can see, over time, do you see how all these tiny, small halos kind of fall into the large, bright dot in the middle of the box? That's how galaxies formed. But that's not a galaxy yet. That's just going to be a single star-forming cloud that produces a primordial star. And primordial stars, we think, appeared 100 to 200 million years after the Big Bang, and they're worth an entire talk on their own. It's really, really interesting stuff. But individual stars formed in the universe before galaxies did. Those stars then congregated through gravity into galaxies. So this is what we mean by structure formation and the universe being hierarchical. So, and I'll just throw up here a couple of slides. So this is a supercomputer simulation of the cloud, primordial gas cloud, that gives birth to the first star in the universe. And as you can see, okay, I forgot. We talk about, okay, so we often talk about light years as a distance scale, right? 6.6 trillion miles. But unfortunately, we astronomers complicate things, and we talk instead about parsecs. Parsec is short for parallax second, and a parsec is 3.3 light years. So when I talk about 100 parsecs here, that's about 330 light years in diameter. That star-forming cloud is about 100,000 to 1,000,000 times more massive than the sun, the entire cloud is. And a primordial star will form at the center of that object. So we have supercomputer simulations now that can take a box that's 1,000,000 light years on a side, and they can zoom in, and zoom in, and zoom in, down to a fraction of a radius of the sun. So think of it as a microscope with unlimited magnification, if you have enough memory on your computer. If you have enough memory in the computer, you can zoom in and zoom in and zoom in as far as you want. And so I've seen these primordial star simulations start in a box of 1,000,000 light years on the side. By the end of the simulation, they're watching sound waves rattle around a Jupiter-sized object at the center of the simulation. It's pretty amazing. And so what you're seeing here is you're zooming in to smaller and smaller scales in the cloud, to where you can see at the very center a primordial protostellar disk that builds up a star. Okay. And here's a zoom-in movie that kind of shows you the power of these so-called adaptive mesh refinement techniques, where now you're in the protostellar core at the very center.
Is that because as we do collapses, you can do all the stuff that's outside a certain region?
Yes, it is. So the deeper you go into the collapse, the faster the collapse happens because the densities are higher and the speeds of sound are faster. So did any of you ever see the movie Inception? Oh, if you haven't seen it, go rent it. It's a really good movie. But do you remember in the movie about how they had multiple dream states? And the deeper that you went in the dream states, the faster things happened in that place than in the level above you? That's exactly how the collapse of the star-forming cloud happens. So the star forms in the center, while the outer region of the cloud barely realizes the center has begun to collapse. Yeah. Okay, so let me just point out a couple of points here. So I talk about quasars and supermassive black holes. So do you know what the difference between a quasar and a supermassive black hole is? they're the same thing. A quasar is just a black hole, a supermassive black hole that's actively accreting gas, so it's bright. So the black hole at the center of our galaxy is not accreting, probably, thank goodness. It's not accreting quickly. But if a collision with a nearby galaxy happened between us and another nearby galaxy, that collision could tip gas into the center, into the black hole at the center of our galaxies and fire it up again. And we start getting radiation out. So did you know that the Milky Way is on a collision course with the Andromeda galaxy in about 5 million years? So just just for fun, several years ago I saw this paper on AstroPH. AstroPH is the website where all the new astronomy papers are presented every day. And these guys, I know they were doing it for fun and games. What they did was they calculated the probability that the solar system would remain in the Milky Way versus go off in the Andromeda galaxy after the collision. They found that there was a 5% chance we would go off in the Andromeda galaxy. And incidentally, when two galaxies collide, you know that none of their stars actually collide. Because the space between stars is too large. But the gravity, the galaxies themselves are torn apart because of gravitational tidal forces, and they're quite spectacular. But anyway, quasars are actively accreting supermassive black holes. And we have now, so I said over 100 quasars have now been found at redshift greater than 6. Well, redshift greater than 6 means less than 1 billion years after the Big Bang. That number is now 160, over 160. Supermassive black holes have been found in the first 1 billion years of the universe. And one of the great questions of astronomy is how they formed. So let me tell you what we think are the formation pathways, or the possible pathways. So some people think that these supermassive black holes could have formed from the collapse of primordial stars. You know how I just discussed primordial stars? What we think, the numerical simulations suggest that the primordial stars were kind of dinosaurs. They were very massive, typically tens to hundreds of times as massive as the sun. Well, any star greater than about 12 solar masses will collapse to a black hole. So the idea is, well, maybe these quasars started life as a couple of hundred solar masses from the collapse of a primordial star at cosmic dawn, and then it just grew very quickly. It's a possibility, but it's difficult. And the reason for that is because the black hole, after it's born, it has to feed very quickly. They're hungry. And the only way it can reach 1 billion solar masses by redshift 6 is if it's accreting continuously at something called the Eddington limit, which I won't go into now, but it's kind of a speed limit for the growth of black holes. It's not a firm one. Black holes can grow faster than the Eddington limit, but it's hard. And unfortunately, when these black holes are born, they're born starving. Because the stars are so massive, their radiation kicks all the gas out of the cloud that gave birth to it, and the black hole is just born isolated. So it can't grow quickly. So never say never, but that has caused people to look at, well, is there a way that these black holes might have been born at much higher masses than we expected? Not a couple of hundred solar masses, but maybe a couple of tens of thousands, or even a couple of hundreds of thousands of solar masses? And the answer is yes. We actually now have kind of a robust context, or robust reasons for thinking that the universe, the primeval, primitive universe, could have produced stars that were 100,000 solar masses, 100,000 times the mass of the sun. And these are just supercomputer simulations of scenarios that might have presented those, that might have created those. I won't go into those now. But let me show you a movie. Let me explain to you what you're going to see. Remember I told you about primordial halos? And how they were the sites of first star formation in the universe. Well, some of those halos didn't form stars until they were 100 times more massive than I was talking about. And there are a couple of reasons for why that can happen. But when they did, reach a certain mass threshold, it's like you can throw a light switch on and they begin to cool catastrophically. And when I mean cool catastrophically, gas can fall into the center of that small protogalaxy at a solar mass per year. And what does that gas become? Does it just collapse to a black hole, or what happens? And what numerical simulations show is that gas flattens into an accretion disk. And that accretion disk is enormous. It's 6 light years across. And it builds up a 100 to 200,000 solar mass star in just a few 100,000 years. And that star is so massive, it collapses under the weight of its own mass, and it forms a black hole through something called the general relativistic instability. And if you want to know about the general relativistic instability, it's really cool. And I'll tell you about it later, like in question and answer, if you want to hear more about it. But we think that that scenario could have produced 100,000 solar mass black holes at birth. Then you're off to the races, because it's 100 or 1,000 times more massive than a black hole due to a POP3 star, primordial star. And that object can grow a lot faster from the get-go. And objects like that can, numerical simulations show, reach 100,000 solar mass, or a billion solar masses by redshift 7. But let me detour. I think I have enough time to get through this quickly. Yeah, let me go ahead and go through this quickly. What does 100,000 solar mass star, what would that thing even look like? You know, like that was the first thing I wondered about when I heard about these scenarios. And the fact is, nobody modeled it on a computer until just a few years ago. And so it turns out that they can have diameters that easily go out to the orbit of Jupiter and maybe out to the orbit of Pluto. And they're cool and red stars. They're not hot and bright stars. Well, they're bright, but they're cool and red. And they can have, even though they're cool and red, a few thousand degrees Kelvin, they can have luminosities that are 10 billion times that of the sun. So they're very red objects, but they're very bright ones. And it turns out, my student Marco Sorace and I just published a paper in the Astrophysical Journal Letters that show that the next generation of telescopes will be able to see these stars and be able to identify them. So the other thing to keep in mind is that these stars, because they're cool, they don't have a lot of ultraviolet radiation. And because they don't have ultraviolet radiation, they cannot halt the flows that are piling gas onto them. So these stars, they're born, they evolve, and they die under the heavy accretion flows that create them. And the reason they collapse is because when they get to about 100,000 solar masses, their cores are so hot that their photons, and they're buzzing with so many thermal photons, that the thermal photons contribute to gravity through general relativity. They actually strengthen gravity. It's a minute effect, only 0.1%, but it's enough to tip the core over the cliff of collapse into a black hole. And then soon thereafter, the rest of the star follows.
So what's the lifetime?
Very short, 100,000 to most of 1 million years. And most of these stars don't blow up. They collapse to black holes. Although we did find one star on supercomputer, 55,000 solar masses, that does blow up. And if there's time during Q&A, ask me about that, because the explosion of that star tears apart the galaxy that gives birth to it. Imagine 10,000 type 1a supernova going off in one place. Explosion of a supermassive star. But the great majority collapse to black holes. And so this is just a quick figure that shows, based on how quickly the star accretes, what its mass is at death. And as you can see, even for relatively what we would call modest accretion rates, the star gets over 100,000 solar masses and then collapses to a black hole. So we think these could have been the seeds of the first quasars. So I'll skip that slide because I've already discussed it. And now let me finish my talk with numerical simulations of the formation of these quasars and supercomputer simulations. So a couple of years ago, a postdoc that I supervised at Los Alamos and I built these supercomputer simulations of the birth and formation, evolution of these direct collapse, these supermassive star black holes, down to redshift 7 and 6 to see if they could reach 1 billion solar masses. And we were really proud of these simulations because for the first time, and you don't have to understand, or I won't go through all of these bullet points in detail, but for the first time in a supercomputer simulation, we had X-rays coming up from the black hole. We had star formation in the host galaxy of the black hole, and that's important because star formation, those stars blow up, and those supernova waves rattle the black hole, and they can disrupt its fuel supply. And so we have to get that physics into the simulations to see how fast these black holes really grow in the models. And for the first time, we were able to do that with enough resolution to see what happened. And what we found, let me show you, is this is the bright evolution of the bright nebula that the X-rays of the quasar creates. And at redshift 17, that's at about, redshift 17 is about 300 million years after the Big Bang. You can see it's really tiny. Then at redshift 9.5, it's a little tiny bit bigger. But then by redshift 7, it is 6 million light years in radius. 6 million light years in radius. So these things put on an incredible light show in the early sky, early universe sky. And then the plot, on the right shows you how quickly the black hole grows. And you see those little black dots with the error bars. That little black dot shows you that the path, the growth curve of the black hole cuts right through the center of J1120, which is a 2 billion solar mass black hole discovered at redshift 7.1. So the numerical simulation, one of the things that you find out in a hurry in a supercomputer model is you never just believe your own simulations, because codes can go wrong, simulations can go wrong. But in this situation, or in this run, we reproduced the mass of a quasar and observed one, but we also reproduced on the left, or on the right here, the star formation rate in the host galaxy. And that was key, because that meant that we got the star formation in the galaxy right, and how the black hole and the star formation regulated each other down through cosmic time. That was key in the simulation to get that right. But we also reproduced the size of the nebula created by the black hole, which you can see in an image here on the left. And then metallicity. So remember I mentioned that supernovas produce metals. Well, the black hole triggers really vigorous star formation in the galaxy through physics we don't have time to go into here. And that really vigorous star formation pollutes the host galaxy of the quasar with metals. And by less than 1 billion years after the Big Bang, there are as many metals in that galaxy as there are in the Milky Way galaxy today, 13 billion years later. That's how quickly, these were very, very alien environments to what we see in the universe. A lot of things were going on in these host galaxies, and metals built up very quickly in them. And then lastly, we've actually calculated spectra for these galaxies, and we found, for these quasars, and we found good agreement. So let me just conclude my talk there, that we now believe that we can explain how the earliest supermassive black holes in the universe formed. But these are supercomputer simulations, and sure, we reproduce the properties of 1 or 2 quasars well, but that doesn't mean that we're right. What we need to do now with the next generation of telescopes is catch these black holes in earlier stages of their growth. And right now, the James Webb Space Telescope, which will go up in 2020, which will replace the Hubble Space Telescope, The European Extremely Large Telescope, now being built in Chile, will have a 40-meter mirror. And then Euclid and WFIRST, two near-infrared orbital missions that will go up above the Earth's atmosphere. All of those observatories will be able to probe the evolution of primordial quasars back to much earlier epochs than we can do today. So people like me are waiting for those observations with bated breath because they are going to test and challenge our models. And that's how we progress as a community. So thank you very much.
Dr. Dan Whalen, thank you very much for a very unscary approach to some very scary physics. Certainly I understood it. I've come across before. Tell me, you mentioned that primordial stars could be a whole other talk by itself, and the vigilant amongst you will have noticed that we have a talk coming up by Dan's colleague, David Wands, on 1st of April about the very, very early universe, so I guess that might be coming into that kind of area?
No, actually, he's going to talk about the really early universe, like the
Right,
first couple of seconds of the universe. But it's super interesting because he'll talk about inflation and how the universe expanded faster than the speed of light at very early times. So, and David Wands, I'm really not talking up a colleague because he's a world expert on inflation. So you're going to hear from one of the top 10 people in the world about this.
So we're going to have a 45-minute talk in the first few seconds. Very good. Looking forward to that. That's on the 1st of April. But our next talk is on March the 4th. And it will be posing the question, what is a quantum internet? They'll be looking at demystifying quantum computing and quantum communications. So that's our next talk back here on March the 4th. We're going to take a 10-minute or so break now so people can go to the bar and get some more refreshments. And after that, we'll come back down to take your questions.
I'd like to ask you a question, please, about dark matter and dark energy. I think it was implicit in what you said that dark energy shares a dark matter shares a characteristic of normal matter, that it wants space and time to produce the effect of gravity.
Yes.
Is there any evidence to indicate that there's an interchange between dark matter and dark energy in the same way as there is between normal energy and normal matter?
No, not yet. I wouldn't be surprised if theorists have been thinking about a possible connection, because once dark energy exploded onto the scene back in the late 1990s, thousands of papers have now been written about it. And the reason thousands of papers have been written is because our observational constraints on that cosmological expansion aren't good enough to rule out all those possibilities people have been talking about. So I wouldn't be surprised if somewhere people have talked about dark energy, dark matter interaction. I haven't heard anything about it myself.
Thank you.
Another question.
When I read what you were going to present us with and guessing at what the origin of a very early supermassive black hole might be, I wondered if it couldn't be effectively a white hole, something which was a particularly dense part of the early universe, which in effect hasn't expanded yet. And you can't tell the difference from the outside sort of what between a white hole and a black hole.
Ah, okay. All right, if you give me 60 seconds, I can address this. So we didn't have time to go into the structure of a black hole, but classical general relativity, and when I say classical, I mean there's been not quantum. No quantum mechanics. It's purely non-quantum mechanical general relativity. Suggests that if a star is not rotating and it collapses to a black hole, that's the simplest case of a black hole you could have, because you have an event horizon that surrounds a point of infinite density because it has all the mass of the star, but it collapses literally to a geometric point. That's what classical relativity predicts. Well, that's got to be wrong. Because if an infinity appears in your equations, it means your equations have broken down. Your theory does not accommodate what's happening. But if we stick with that story, what's the next simplest case you can imagine? A rotating star. So if a rotating star collapses to a black hole, and again, you have an event horizon, but it has a much more complicated structure because you have an event horizon that's surrounded by something called an ergosphere, which we won't go into. And instead of having a point singularity at the center, you have that singularity is a closed loop, it's a ring. And what the classical theory predicts is that if matter falls along the axis of the black hole and through the ring, it could appear in a distant point in space-time through something called an Einstein-Rosen bridge. Well, if it appears, if it comes out of an Einstein-Rosen bridge, that would look like a white hole that you're talking about. The issue with that is nobody's discovered anything that looks like a white hole yet. So we don't understand.
I wasn't meaning a white hole. I wasn't relying on an Einstein-Rosen bridge because I went so I wasn't. If you had a very high, an unusually high density in the initial expansion, then the time would move slower for that. It would expand, but it would expand, but viewed from a distance, it would appear to be expanding slower.
What is it that's expanding here? Let me just make sure I'm on the same page with you. What are you talking? What is expanding?
The initial Big Bang.
Oh, okay. So now we're talking about the Big Bang.
Yes.
Okay, it's the expansion of the universe. Got it. I'm with you. And so
instead of a dimple, you've got a very large volume with a higher mass. I wouldn't like to guess how much higher it has to be than the normal. Then that would expand. That would expand slower. I mean, locally, it would be able to be expanding quicker, but of course, the time moves slower in dense portions, and so from a distance, it appears to expand slower.
come to David Wan's talk about this because he's going to talk about this physics. But let me just mention one thing about what you're talking about. So when you look across the sky on large scales, sure, galaxies are distributed in this cosmic web, right? But the cosmic web on very large scales, it looks pretty uniform across the universe. And the question is, and the uniformity extends over angles on the sky that could not have been connected by the speed of light. That's important. What in the Big Bang could have caused that? The only thing that could have caused that we understand is an early phase of expansion that's faster than the speed of light that could preserve that uniformity over their scales. You have to have a superluminal expansion that I think would prevent what you're talking about from happening because the densities would go down too quickly because of that. But talk to David Wan's because I think he can probably do a better job.
Thank you.
According to that question, do we have any more questions?
Yes, perhaps I could ask. Rather more mundane question, I'm afraid, but you mentioned that the next generation of telescopes will give you your ground truth for your models. But I wonder, before that, I mean, at this stage, how much confidence do you have in your models? I suppose you've done sensitivity analysis and things like that. Are you pretty sure that they're an accurate reflection, or is there a lot of scope for possible error?
No, this is a really good question. And so we talk about sanity checks, right? Like, are your models sane? And you constantly have to do this. And our models so far, our models pass all the sanity checks, but the physics I told you about, that I listed in those bullet points, they were a good start, but they're not complete. So for example, one of the things that we didn't take into account, so when I said we modeled X-rays streaming out of the host galaxy, we only included opacity due to hydrogen helium. we did not include the opacity to the metals produced by stars over time. That's going to change how quickly X-rays get out and how they heat the galaxy, and in turn affects later generations of star formation. So these are good models, but we have not killed the subject like with them. There's a lot, and I'm not discouraged by that because I just see future PhD projects. There's a question in back, I think, that might have gotten.
Oh, yeah.
You mentioned just now that in the very early stages of the Big Bang, it was actually expanding at a speed greater than light, which is interesting, but I thought the theory was that nothing could move faster than light. But you also, earlier on, said that in the very far distant future, we will not be able to see any other galaxies because they will be moving away so quickly that light won't be able to reach us. Does that not imply that it gradually expanded at the speed faster of light, then slowed down, and it ultimately will speed up again?
Well, let me answer your first question first. So, and I'm glad that you asked it because one of the two principles of special relativity, even not even general relativity, is no object with a rest mass can travel at the speed of light, and only photons can travel at the speed of light. And so, how can the universe itself expand faster than the speed of light? Well, it turns out that the speed limit only applies to objects within the expanding mesh of space-time itself, not how quickly the mesh itself expands. So space and time itself can expand faster than the speed of light, but always in such a way that the speed of particles trapped within that mesh can never exceed the speed of light. And that's how that can work. So incidentally, I don't know if you've heard about Cuvier drive. Have any of you heard about this possibility of breaking the speed of light? It's the so-called Cuvier drive. Well, the way it proposes to break the speed of light is by warping space and time around the spaceship, so that the ship is always less than the speed of light within the bubble, but the bubble itself advances faster than the speed of light. It's the same principle. Now to your second question about the expansion history of the universe. Like, it expanded, so at very early times, the current models that we think are correct, indicate that, right after the Big Bang, at very early times, we had this exponential growth driven by inflation that was faster than the speed of light. And then it slowed down. So it slowed down for a while. And then, okay, let me see if I can get the results right. There are two components to the universe, radiation and matter. So at early times, radiation, photons, controlled how fast the universe expanded, up to a certain time, when matter took over. Matter then controlled the expansion rate of the universe, and that's when it slowed down. Now, as matter becomes more dilute because the universe is getting bigger, dark energy is going to start dominating the expansion rate of the universe, and is beginning to dominate already because it's accelerating the expansion of the universe. Does that answer your question in there somewhere? Or?
Yes, it does. I'm just wondering what the dark energy was doing in the interim.
It was always there, but radiation and matter dominated it at early times of the universe, but in the end it will win.
Does this mean that matter has actually turned back into energy?
No, the matter and energy, or what we call mass energy, is all still there. And even dark energy, we think, is a form of energy. It just has very unusual properties that cause the expansion to accelerate rather than slow down. So dark energy is really strange because it exerts what we call negative pressure. So like if you blow up a balloon and you try to compress it, it fights back, right? That's normal pressure. Positive pressure. Negative pressure is you press on it, it collapses even faster. And that's one of the reasons dark energy is so strange. We don't understand what type of energy could be doing it. But we infer that it's there because of the dynamics of expansion we observe. We infer it has to be there.
Thank you.
Okay.
Just a quick follow-up. So you mean, in the end, the dark energy will push the mass in the universe apart faster than the speed of light?
I believe so, yes.
Can you comment on the LHC? They're firing charged particles. It can't accelerate particles that are uncharged, and it looks like dark matter is not charged. So, what are their chances of doing it, or are they not mission impossible?
Well, so the idea was that they would smash the particles together, and from the energy of the collision, dark matter particles would freeze out of that energy. And the problem is once you get a dark matter particle, you can't follow the particle itself because it doesn't interact with your instrument. It gets out before it can interact. You infer its properties from the fact that after the collision, you're missing energy and you're missing momentum. So you infer that the missing energy and momentum had to be carried away by a dark particle. And it's difficult. The other attempt, the other angle that they're going at is so physicists have built super cooled crystal detectors. And the idea is this: if you can get a super cooled crystal detector far underground, away from cosmic rays, some dark matter theories predict that some dark matter particles will spontaneously decay through the weak sector. In other words, through the weak nuclear force. And if they do, and they happen to be close to an atom in that crystal, they'll exchange a quantum of sound with the crystal called a phonon, and they can detect the phonons. So that's been the main experimental approach to try to directly detect dark matter. And the problem is it's very difficult to do that because you've got to get the crystal cold and you've got to get it away from all sources of radiation. Because cosmic rays, remember, can penetrate hundreds of meters of Earth.
Well, that's why it's all available in deep.
Exactly. So the dark matter physicists, we joke that they're kind of like the fusion people. They keep saying that fusion power is right around the corner, and they've been saying that for 60 years. Dark matter people, experimentalists, keep saying, well, we think it's right around the corner. But you can't make fun of them because eventually we'll get fusion to work, and eventually somebody will find dark matter, and whoever does will get the Nobel Prize.
Slightly different subject. I was wondering, you mentioned about accretion disks.
Yes.
And what we see with galaxies is that the baryonic matter forms into disks, basically. That's what happens in planetary systems and so on. I was just wondering if the same thing happens with dark matter, because generally dark matter is a sort of a blob that surrounds the galaxy rather than something that's called disk shaped.
Yeah. So, dark matter does accumulate at the centers of galaxies, and but it doesn't form disks in the same way the gas does. And there are a couple of reasons for that. Partly because it's collisionless, because dark matter particles don't collide with anything, so that means they don't experience viscosity, which means they don't have friction, which is part of the thing that forms accretion disks in the first place. So a typical dark matter halo that forms one of these, what we think supermassive stars, it has a radius of about 1,000 light years. Once you get into the central few light years, the gas dominates the gravity, not the dark matter. The dark matter gravitates dominates gravity at larger radii, but not at the very center of the galaxy. So, that's how it works.
But if the dark matter was rotating, it doesn't need this viscosity effect to form a disk.
That's right. So you could form there. I mean, in principle, you could form. You could have dark matter particles kind of orbiting in a disk, but they wouldn't form spiral arms, and they wouldn't lose energy because they don't collide with other objects.
We have another question. From the younger members of the audience? Looking terrified now.
So incidentally, I should mention that this room could be filled to the ceiling with 500 tons of dark matter. We could open a door, walk in, never be aware of this here. Because for us to be aware that it's here, we have to exchange photons with it, and dark matter literally does not do that.
I don't think we could say that to Hampshire County Council because they have to be able to account for everything, and there's no amount of dark matter in here, and they can't measure it. That'd be really scary.
So if the dark matter is not interacting with the normal matter, how is it pushing normal matter apart?
That's dark energy.
Okay.
Yeah, which is the different, yeah. And dark energy pushes both the matter and the dark matter apart. Now, one thing I should tell you is, when I said eventually cosmological expansion will carry away all the other galaxies, I should have excluded all the galaxies within our local group. Because those galaxies, like Andromeda, M83, the satellites galaxies, those galaxies are close enough to us that our mutual gravity binds us together. We say that they're decoupled from the Hubble flow. We're locally decoupled. So this is why the expansion of the universe doesn't expand the Milky Way apart too, because the Milky Way itself is internally cohered by gas and dark matter. So are the local galaxies that are bound to us by their gravity. But very distant galaxies will be carried away from us.
That poses a question. So that when you present it, there's some sort of long distance effect. This expansion is long range. Can you hear what I'm saying?
Yes.
Yeah. If that expansion is really long range, what's happening locally? Is there no expansion sort of locally, or is it too small to measure?
It's too small. So think of the local group as an island of galaxies decoupled from the expansion of the universe as a whole. But more distant galaxies are not that tightly coupled to us, and they'll be carried away by the expansion of space-time between us.
But that expansion in space-time is the same everywhere.
Yes. Well, on large scales, yes. On local, smaller scales, no. You have islands of bound objects, yes.
They're contracting through gravitation. But that's a different phenomenon to the dark energy.
Yeah, so locally, gravity beats dark energy.
Yeah, so space gets, point something % bigger.
Yes, but globally it loses.
We don't notice that, but we notice it over a very long distance.
Yes. Now, there is one thing I need to tell you about, and that is there's a tendency for the public to trust scientists too much. And what I mean by that is this. If scientists are being honest, they don't talk about the truth. They talk about models. Right? We talk about models. Because, and Einstein put it best, he said, I can never prove that my theory is correct. I can only disprove it through an experiment. Right? So down through history, this has been really important. So you remember back in the mid-1800s, people believed that there was this luminiferous ether. And it was through ether that light waves propagated, right? Because after all, they figured out, they knew that light was a wave from optics. And nobody had ever seen a wave in nature that didn't have some medium propagating it, right? Like sound waves or water. So people thought, well, there's a luminiferous ether. Well, Michelson and Morley built an interferometer, and they went to the top of a mountain to measure the change in interference patterns due to the luminiferous ether over 6 months. And 6 months later, they went up to their instruments and they found no change. That meant there was no ether. That one negative experiment led to the relativity revolution. Negative experiments are the most important ones in science, right? Yeah. So you can only disprove a theory, you can't prove it in the end. So, look, 20 years ago, scientists were saying the expansion of the universe is slowing down. Well, because it has to be. That's the only thing that makes sense. Until the Type 1a supernova measurements got measured, right? So, I would say we think dark energy is real, but that's because that's what our current observations tell us. And we could come back later and find that maybe there were some systematics in those measurements that led thousands of people off on a wild goose chase. And really there is no dark energy. It could still happen now. My colleagues would chastise me for saying that in public, but it could happen. I mean, let's be honest.
So how many data points did they gather in Type 1a?
So in the original measurements, they took a couple of, like, I think on the order of 100 to 200 supernovae back in the mid-1990s. And that was a lot. Why is that? Well, there's only one supernova per century in a galaxy. So if you want 100 or 200 of them, you have to look in a lot of galaxies. And that means you have to look on a large part of the sky for a long time. Well, there are telescope review boards that look at your proposal and say, why am I going to give you this much telescope time to do this project when so many other people want to use the telescope? I mean, think about James Webb, the JWST. Think about how brutal that process is going to be, that allocation process. But they got the time. Now, so there's a new telescope called LSST, the Large Synoptic Survey Telescope. It will see first light in 2020, come fully online in 2022. It will look for hundreds of thousands. It will find millions of supernovae out to redshift 1. And that will, I think, will tell us a lot more about dark energy. Sorry to lead you kind of on a long discussion around that, but it's really important. Don't take science as the gospel. Because it can take one good experiment that knocks an entire theory down. And actually, life is most interesting when that happens, because it leaves. So, in my opinion, quantum mechanics itself right now holds the seeds to its own destruction because of these issues with action at a distance and inconsistency. We're not there yet. And that's cool. It means there are lots of awesome discoveries to be made. Anyway, not to go on too long.
Some other branches of science, particularly pharmacology, have a lot to learn from the value of a negative experiment and not pushing them as well.
Yeah.
Is it difficult to get publication of negative results in cosmology, or is that seen as?
Oh, yeah. So last year, so there are 3 main astronomical journals that we publish in. So there's the Astrophysical Journal, which is American, and early in my career I published there mostly. Monthly notices of the Royal Astronomical Society, which is here in Britain, and then Astronomy and Astrophysics, which is a European journal. But then there are kind of like the big, so then there's Nature and Science. I don't know if you've heard of those 2 journals. So scientists have a love-hate relationship with Nature, right? Nature journal, because everybody wants to publish there, but it's so political that you can get shot down. And there's a joke with my colleagues where they say, "Are we really sure this result is wrong that we want to publish in Nature?" And so last year in Nature, some people published a letter saying that the whole Type 1a supernova measurements were wrong. They were just seeing systematics and there was no dark energy. And like those guys, let me put it this way, if I were going to publish a paper like that, I would make really sure I had not made any mistakes. Because once you publish a paper like that, you have an orthodoxy in science, right? And those people sit on the grant panels that dispense money. They sit on the panels that dispense telescope time. And if you're wrong about something like this, where you're telling hundreds of people that they've been wrong for 20 years, you're going to have a hard time ever getting another grant or telescope time. But the paper got published because the editor of Nature likes controversy, likes to stir the pot, and so that's why. But I heard my colleagues, one of my colleagues at ICG said, my undergraduate students could have done a better calculation than those guys, and it got into Nature astronomy. So it happens, but you have to be careful about that.
I think we better wrap up there for now. But Dr. Whalen, thank you very much again for a very engaging question and answer session, as well as a very enlightening talk.